Hello everyone. In this session, I'm going to look at the classification of the data using naive Bayes kind of an algorithm. So this uses the concept of Bayes theorem as is clearly seen from the name itself. We'll see how this theorem is getting used in terms of doing the classification of the data. Now, this is also another type of classification algorithm. Classification itself is one of the two major components of supervised learning in machine learning. One being the classification, two being the numerical prediction, which is what can be accomplished through regression kind of model. So within the classification, again, there are many algorithms which help in the classification of the data, and naive Bayes is one such kind of an algorithm. So we'll see what is naive Bayes all about, in which context we need to use this naive Bayes algorithm, what is the basis, what are the fundamentals that are associated with naive Bayes, how does the Bayes theorem come into picture, what are the basic concepts associated with Bayesian methods. So a few important definitions from the world of probability, which is the conditional probability and the Bayes theorem, we are going to discuss about them. The algorithm as such, naive Bayes algorithm, right? How do we implement that in R? How does the naive Bayes classification actually happen? Right? What is the strategy? What is the logic with which naive Bayes actually classifies the data? To a large extent, naive Bayes actually works with more and more categorical kind of variables. We would be seeing that. But if at all I have numeric variables as a part of the data, how does the how do we really make the necessary modifications to make sure that I can implement naive Bayes on my data? Once the basic conceptual understanding is done, we'll take up an example. We'll take up a data set. We will try to train our model using the naive Bayes algorithm. We'll try to create a model, and then we'll try to test the model as well. So, first thing we have to understand it, if something is a probability estimate. See, many a times we use these kind of estimate. There is a 60% chance that I will pass the exam. There is a 75% chance that it will rain today. So these are called as probability estimates. So when we are arriving at these estimates, we are arriving at based on the probabilistic methods. So there is something relating to uncertainty. So probably it's like this: when the weather is similar to this earlier, probably on 75% of the days it has rained, right? Earlier, historically, when I look at the weather, or historically when I look at my question papers, when the question paper was similar, in 60% of the cases I have passed the exam, and in 40% of the cases I have failed. So which is what will give me a kind of an indication to make the prediction for the future as well. So we are making a probability statement because in some cases there was success when everything was similar to the current situation. From the historical data, there was 60% of the times when I was successful, 40% of the times when I was a failure, or 75% of the days where there was a rain, 25% of the days there was no rain. So that is how we use the data based on the past events. Historically, whatever the data that we have collected, we will try to create some kind of proportions, percentages based on the past data, and use that information to extrapolate the predictions for the future. Naive Bayes is actually working at that layer itself. So there is the use of probability. The concepts of probability are used quite heavily by Naive Bayes for doing the classification of the data. So we need to have good understanding on the different principles of probability. And before I actually implement Naive Bayes, I need to have a good visualization of the data. And here I would really look at an example of text data. If I really have to use Naive Bayes, right? Naive Bayes is very much applicable even for analyzing a regular tabular data as well. But in case of text data analysis, we use it quite frequently, one of the major applications. So I would like to take the example of a text data, wherein we are looking at different kinds of messages. Historically, people have classified all these messages as either a spam or a not a spam, which is a ham. And based on this information, so the historical classification was every message has been classified as a spam or a ham. And based on them, I want to build a model to say what kind of words in the message will make it as a spam, what kind of words in the message will make it as a ham, and based on that I want to develop a kind of a model which talks about what is the probability that if a particular word is included in the message, right, it would be classified as a spam, and what is the probability that it should be classified as a ham. So I need to have different kinds of methods to work with text data. So we'll talk about all those kinds of methods. This could be a part of even text analytics, where I'm doing a thorough analysis of the textual data. Right, we could very well use the Naive Bayes there as well. And we are looking at the R implementation of the Naive Bayes classifier. So these are the various things that I wanted to cover as a part of this session. So initially, getting a hold of Naive Bayes. Whenever we talk about the Bayesian methods, so we are talking about describing the probability of event P of A given another event has occurred. Additional information is provided to me. So whenever we are talking about Bayesian methods, it's more like probability of a particular event A, and how do I revise the probability of this A when I get an additional information. The additional information is given the event B has already occurred. So those kind of conditional probabilities. So determination of conditional probability based on the marginal probabilities is what is the application, or is what is the definition of Bayes theorem and Bayesian methods. So a few quick revision of the concepts of probability. It's a number between 0 and 1. 0 means it's that particular event does not occur. 1 means it's a certain event which is very much bound to occur. And the chance, whenever we define the probability, it's a chance that the event will occur based on a given evidence. So any classifier that is based on Bayesian methods, what it typically does is, first I will provide a training data to it. Based on the training data that I am providing, it will try to compute the probability for each class. So what is the probability that a particular message will belong to a spam, or what is the probability that it is belonging to a ham? And based on each feature, right, I could give each feature separately. So probably if I am using a word called call in my message, so what is the probability that it belongs to a spam? What is the probability that it belongs to a ham? So we are trying to calculate the observed probability. So because this is all historical data or the training data. Based on the training data, I am calculating the probability of each class based on each feature. And based on this, a model is being created. So these observed probabilities are typically used to predict for the new features. If I'm talking about a new mail or a new message that I have got, based on the quality of the words that are used in the mail or on the message, I would like to classify it as a spam or a ham. So there are many applications to it. So especially for identifying the spams and hams, coming out with filtering the messages, mails, etc. There is a lot of, and even the author identification, topic categorization, it has a lot of applications in text analytics, though I can very well use it even in numerical feature based classification as well. But there is a lot of application in the text analytics. So we will be so here we would be the reason why I have picked this example here is, on one side we would try to do a basic text analytics as well, where we will use the different kinds of text related functions to summarize the textual data, and at the same time on that textual data I can implement the naive Bayes algorithm to classify that particular textual message as a spam or a ham. So I can very well apply it in the problems where numerous attributes, I have different kinds of variables. The information of the different kinds of variables should be considered simultaneously. All the variables are influencing, there are different kinds of variables which are influencing the class of the mail or a message, and all of them have to be taken together simultaneously to predict whether a particular message would be a spam or a ham. So this is where naive Bayes comes more and more handy. Coming to some key concepts associated with the Bayesian methods. The key idea is any estimate of the likelihood of an event occurring. So the probability of the occurrence of A. The estimated likelihood should be based on what is the evidence that I have at hand. So based on the existing data, so this is what we call as the priori probability. Based on the existing evidence that I have, on that existing evidence, I am trying to find out the estimated likelihood of the event. So the probability wise, I am estimating it from the observed data. So the total number of outcomes and the total number of favorable outcomes in the process. So we can have some events which are mutually exclusive, exhaustive. We know all this theoretically. I am not dealing with these concepts theoretically. Events which are occurring at the same time are called mutual. Events that do not occur at the same time are called mutually exclusive. When I am tossing a coin, if a tail occurs, head will not occur, and if a head occurs, tail will not occur. They are mutually exclusive events. And exhaustive events is, apart from these two, no other thing can occur. So these put together is the total sample space. So the sum of probabilities of mutually exclusive and exhaustive event, the probability of a tail occurring is 1/2, the probability of a head occurring is half. These are mutually exclusive along with exhaustive. So the sum of their probability should always be equal to 1. And another important concept, joint probability. When we are working with several non-mutually exclusive events, A, B, C, D, I am talking about all these various mutually exclusive events. So if some events occur along with some other event, right? Probably if a rainfall is occurring along with the thunder, then whenever a thunder occurs in the future, I may really find out what is the chance that a rainfall will occur. So this is what is the basis behind the joint probability. When I am talking of two different events, So one event has occurred, and this occurrence of an event is influencing the probability of occurrence of another event. This is means by knowing what is when one event has already occurred, we can very well improvise our decision in terms of what is the chance that the other event is going to occur. So we can use Venn diagrams to typically create the overlaps, and we can also find out what is the probability of A intersection B, which we generally write it as probability of A occurring multiplied by the probability of B occurring given that A has already occurred. This is the main basis for joint probability. So we know all the formulas. Even if you don't know the formulas, I suggest that you refer to a good book on probability, because here the main intention is to implement the naive Bayes algorithm. But because these concepts are very much important, I am quickly running through the concepts without concentrating more and more in terms of explaining these concepts to the depth. Similarly, when we say two events are independent, they are unrelated. So in that case, probability of A given B will be same as probability of A only. So which means even if B has occurred or did not occur, the probability of A will not be influenced by the occurrence of B. So whether B has occurred or did not occur, the probability of A will not change. In those cases, we will say A and B are independent events. They are completely unrelated. But if they are dependent events, this is where we will use predictive modeling. If the events are very much unrelated, if the events are very much independent, so if one event has occurred, I can't make any statement regarding the occurrence of the other event. Those kind of events, I really can't use them as a part of my predictive modeling. This is one important statement I wanted to make in case of probability estimates. See, when two events are independent, there is nothing that I can do as a predictive modeler, because the occurrence or non-occurrence of any one of the event has no influence on the occurrence or the non-occurrence of the other event. So there is nothing much that I can proceed by having an information of whether a particular event has occurred or not. But if the two events are dependent, this is where I'll try to model what is the probability of occurrence of one event given the fact that the other event has actually occurred. So only for dependent events we can think of some kind of predictive models, but whereas in case of independent events there is nothing much that we can talk about. Now, definition wise, the conditional probability is the probability that an event A occurs given that the event B has already occurred. Right? So we are talking about the relationship between the two dependent events. Even the Bayes theorem comes out in the same way. So if we have to use the joint probability formula, which I have talked earlier, probability of A intersection B is same as the probability of A occurring and probability of B occurring given A has already occurred. So based on this you can make out that P of B given A is nothing but P of A intersection B by P of A. Similarly, I can write P of A intersection B the other way also. Probability that B has occurred multiplied by probability of A occurring given B has already occurred. Now both are one and the same, so I'll equate both of them. P of A into P of B given A is same as P of B into P of A given B. So from here I want P of A given B, so I'll bring this thing here. So it becomes P of A given B is nothing but P of A into P of B given A divided by P of B. So look at this, P of A given B, which is what is after we get an information regarding whether B has occurred or not. That's the reason we call this as posterior probability. So we are talking about P of A. P of A is by default in the initial itself what is the probability of A occurring without having any information regarding whether B has occurred or not. In general, what is the probability that A is going to occur? The probability of A occurring. So that is what we call as prior probability. Means without any information about the occurrence of B. So so that is the marginal probability of A, which is obtained from my historical data. What is the marginal probability of occurrence of A, which is called as a prior probability. Then we are talking about the likelihood. What is the probability that B occurs given A has already occurred? Right? What is the probability? So if I have to say for this example, what is the probability that a particular mail is a spam given that it contains a word Viagra in it? So first of all, I am taking what is the probability that a particular mail will be a spam, irrespective of whether there is a word Viagra in it or not, or any other word. What is the probability that it is a spam? So this is the priori probability. Then I am looking at what is the probability that any mail will contain Viagra, which is the marginal likelihood of the event P. So what is the probability that any mail will contain this particular word in it? Forget about whether it's a spam or not. Then I am looking at the probability that given a particular mail is a spam, what is the probability that there is a word Viagra in it? So this is like P of B given A. So what we are saying is I can very well find out P of A given B given one the unconditional probability of A, also the marginal probability of B, and along with if A has occurred, what is the probability of the B occurring. So this kind of classification is what we call as the Bayes theorem. So Bayes theorem formula is going more this way. So the mathematical part of it is this. If you want to see some kind of examples, you can refer to some good books on probability. But this is the funda behind which any kind of Bayesian classification models are based. So initially I am looking at what is the probability that a mail is a spam. What is the probability that it contains a word Viagra. I will also take what is the probability that a mail that given that it is already a spam, it contains a word Viagra. And because this information is already there, so these are all historical. If you see in the historical data, what is the probability that something is a spam? So out of 100 mails that I am looking at, let's say 20 of them are spam, 80 of them are hams. So the probability that something is a spam is 0.2. What is the probability that the word Viagra is present in the mails? So you can see out of 100 mails, 10 of them will contain Viagra, 90 of them don't contain Viagra. So basically this is 0.1. Now out of this 20 mails which are spams, let's say 5 of them contain the word Viagra. So what is the probability that given a mail is a spam mail, it contains the word Viagra? So I am coming out as 5 by 20, which is 0.25. Now using this information, I am trying to find out given now this is more like posterior. This is for the future. So for the future, I am saying, okay, I don't know now whether the mail is a spam or not. This is the future part. I don't know whether the mail is a spam or not. I have to classify it. Now the moment it contains the word Viagra, I will find out the probability that it is a spam. So it will come out as 0.25 into 0.2 divided by 0.1. which comes out as 0.5. So there is a 50% chance that it is a spam, 50% chance that it is not a spam. So that's how the classification works, and based on these kind of classification, based on this kind of probabilities, the classification of a particular mail is going to happen using the Bayes theorem. Now this is where the naive Bayes algorithm comes into picture. So it uses the Bayes theorem only. It's a simple application of the Bayes theorem for classification of your data. So nowadays, for doing text classifications, text related models, text related analytics, especially when the classification is purely based on frequency of words, some textual data, nowadays people are using the naive Bayes algorithm only compared to any other algorithm. So that's where I'm saying it has become the de facto standard, especially for text calculation, text related classification. Few advantages: it's very simple to execute, fast, effective. Even if there are some missing data, it will still work. If there are some kind of outliers and some kind of abnormal values in the data, still it will work. Even if the data size is very small, if I just have around 30-40 records also, I can use the model. But of course, if I have large samples, large data set, then it can do a much better job. But it will not fail even if the sample size is much smaller. So that's also another advantage associated with naive Bayes. And so the estimated probabilities can quite comfortably be obtained. The prediction becomes more and more easier. But on the wrong side, there are a few weaknesses also that are associated with the model. The basic assumption that this model typically makes, it says that all the features that you are providing to it, they are equally important. So it cannot say that a few features are highly important compared to the other. Whereas if we see later, we will be talking about different kinds of other classification algorithms, let's say the decision tree kind of algorithms. So there is an option that I can very well see some variables are more important compared to the other. So here the basic assumption that it makes is all the variables are equally important and there is no correlation that is existing between the variables. All the variables are fully independent. This is also another major assumption. So if the variables are highly interlinked or highly correlated, this model will not provide the necessary objectives. So it is not typically ideal for data sets when there are too many numeric features. Again, all are classification algorithms only. But if there are too many numeric features, if the variables are more and more numeric variables, then better don't apply this model. You can think of some kind of decision tree models, which I would be talking of later. If your number of features, more number of numeric features are there. But if more number of categorical features are there, probably you should rely more on the naive Bayes algorithm compared to a decision tree model. And another weakness associated, the estimated probabilities are less reliable than the predicted class. So it can do the class prediction much better, whether a particular mail will belong to spam or ham. It can do the classification much better. But if I want to say what is the probability that it will belong to spam and what is the probability that it will belong to ham, then there will be a kind of issue. The way it computes the probabilities of belonging to the classes is less reliable. So if I want to really look at the probabilities per se, they are much lesser reliable. But if I want to see whether a particular mail goes into a spam or a ham, I can very well rely on the output that is produced by naive Bayes. So the number of assumptions that it makes about the data is very limited. As I have already indicated as a limitation, the major assumption that it makes is all the variables that I am considering, they are equally independent and they are equally important and they are fully independent. In reality, we have to be very careful when we are looking at that particular aspect, because that may not occur in the reality part. Then, coming to the classification using naive Bayes. So it is a likelihood table is always constructed, especially when I am working with textual data. So there is the likelihood table, okay, for each of the words. Right now I have so many messages. From all the messages, all the words are extracted. Now depending on for each of the word, it will see what is the probability that this if for this particular word, what is the probability of spam, what is the probability of ham. So that is the way it keeps learning from each of the words. So it assumes class conditional independence. As I have already indicated, all the events are independent, but if the two words always come together, it does not have a mechanism to handle them. So this is how it actually classifies the probability. So the probability of level L for a particular class C, for each level, right, for each class, so given that the evidence provided by the features, so we already know that F1, F2, F3, Fn are the words that are there. So if words F1, F2, F3, Fn are there, what is the probability that it belongs to class CL? Now using the application of Bayes theorem, what is that we are saying? What is the probability of the class CL actually occurring, which is the probability of the class spam that is occurring? So here we are saying what is the probability that a particular message is a spam given these words are present in the message. So all we are saying is what is the probability of a spam first of all, multiplied by what is the probability given a message is a spam, this particular word is going to occur. So this is what we are calling as a likelihood part. This is what we call as priori probability. And this is what will become the posterior probability, again linking it with the Bayes theorem. So in this, the only small difference that we bring in into the naive Bayes is the Laplace estimator. See, sometimes what happens is if any one of these probabilities is zero from the historic, because these probabilities are coming purely from my historical data. So at any point, if the probability is becoming zero, any one of them, either this or this, for any one of the class, for any one of the features, if the probability is coming out to be zero because of very small data set, the whole product is going to be zero itself. So my overall probability will come out to as zero, because any one of the probabilities out here, whether it's a priories or likelihoods, any one of them, if it works out to be zero, there is a good chance that my overall posterior probability also will come out to be zero. So this is where the Laplace estimator actually works. So instead of wherever the probability is coming out to be zero, just to avoid the multiplication to come out as zero, we are adding a very small number to each of the counts. So here if it is like 2 out of 80 mails in the training data that I have are spams. So what it will do is it will make it as 3 out of 81. It will add 1 extra to each of the counts in the frequency table. Because even if it is like 0 out of 80 spam mails contained a particular word. So instead of putting it 0 and finally saying the probability is 0, it will take it as 1 out of 81, which means it will add 1 to each of the variable, to each of the counts, so that the overall multiplication of the probabilities does not end up into a 0. So when I am setting the Laplace estimator as 1, it ensures that each class feature combination is found at least once. So I can set it to 3, 4, 5, assuming that at a minimum, let's say if that particular class feature combination comes at least 5 times in the data. So then I am setting this as 5. Even if it comes 0 times, 1 times, it will be set as 5. So can be set to any value, and in some cases I can even set it differently for different kinds of words as well. So the one, if I have to really play around with the model, the Laplace estimator is something that I am playing around with. I can change the values associated with the Laplace estimator, so that my different classification proportions will change, and after that I'll be testing it on my test data to ensure the accuracy of the model. And as I have already indicated earlier, if there are so many numeric features in the data, probably I should not use naive Bayes, because as far as naive Bayes is concerned, it wants every feature to be categorical, because based on that only it will produce the combination of the class and the feature values in terms of a matrix. So it actually, truly speaking, it does not work with numeric data. But if at all my data is numeric, I will, if I have to still use naive Bayes, better I convert them into categories by doing a binning. So basically I come out with class intervals. So if a data is between this and this class, it is group 1. If the data is between 20 and 30, it's one group, G1. 30 and 40, it is G2. So I am creating some kind of categories based on the intervals associated with the class. So when there are large amounts of training data, I am compressing all those training data into a few set of groups. So I can very well specify the cut points where different groups have to be created, and different levels are being created based on these kind of cuts that are there in the data. So otherwise I can create them into quantiles, probably let's say quartile Q1, Q2, Q3, Q4, some such kind of classification also I can very well do on the data. But I have to discretize any kind of a numerical variable if I have to use naive Bayes algorithm for the classification purpose. So when I am trying to discretize, when I am trying to create a group from the numerical value, obviously the information is reduced, right? Because even if I am putting a group as 25 to 50 as group 2, so even if the value is 26 or 49, both of them are being called as group 2. So the significance of the values is actually going down. So there is a lot of information reduction that happens, but at the same time, the positive side is I can still use naive Bayes for the classification purpose. So I should be able to strike a balance. So if the bins are very few, categories are very few, then there is a very big range that is being present, because of which the information reduction is too high. Even at 26 and 49 are treated in the same manner. So I would be losing a large amount of information heavily. But if there are too many bins, then the number of categories is too high. Probably there is a possibility of many zeros coming up, and my Laplace estimators have to be set for each one of them. So the counts will get completely distorted in the process. So I have to really strike a balance between how many bins I have to typically create based on this particular data, so that the learning is much appropriate, and even the prediction is much more appropriate with the data. Alright. So now let's move towards an example where we will take a set of SMS data. Right, we'll have a CSV file which has a big list of SMS data, and those SMSs are typically classified as either spam or ham. Already the classification is done. So based on that, let's do the learning through the naive Bayes. So load the data containing the SMSs and their classification. So let me use the R for that purpose. So it's there as a part of my SMS underscore spam.csv file in my R datasets folder. So I have loaded it. So let's try to understand few basic aspects of it. So I am doing a dim. So it contains 5559 rows and 2 columns. If I want to see what are the names of the columns, I am taking the names which says there is a type which is a spam or a ham, and there is a text. And probably if you are looking at the structure also, the structure of spam, it is like the first one is a factor with 2 levels, ham and spam. The second one is a factor with 5156 levels. Each one is a separate treated as a separate outcome, separate message. So this is where we have loaded all of them. But at the same time, I didn't want this to be a factor, especially the text. I wanted it more like a character itself. So that's where I'll try to change it. Spam dollar text is nothing but as dot character spam dollar text. So I'm converting the factor back into character. I'm converting the factors back into character. So I could look at the head just for a confirmation of what is there as a part of the spam. I could see that the first one is something like this. Hope you are having a good week, etc., etc. So that's a text. Now if I am looking at the structure associated with spam, I could see that the first one is a factor, the second one is a character. Okay, these are the messages. So naive Bayes classifier will take the advantages of the patterns in the word frequency. So it will look at different kinds of words that have occurred in the messages, and based on the words that have occurred, it will look at the patterns of words. So what proportion of a particular word occurring in a message is it treated as spam, and what proportion of them are treated as ham. And based on that, it will determine whether the SMS messages, any new SMS message that we are talking of, would it be classified as a spam or a ham. So the overall classifier will compute what is the probability of a particular message being a spam or a ham given the evidence that is associated with all the words that are there as a part of the message. So that is how the overall model will work. So let's try to build a model which you can very well understand. Based on once you go ahead and build the model, we can very well understand what is the way this whole analysis is going out like. So exploration, first of all, right? First the data is loaded, then we are looking at the data more and more in detail. So I have to process the raw data for the analysis, because here I have it just as 2 columns, one containing the text, the other one is containing whether it's a spam or a ham. So when we have to prepare the test data, it's a big challenge. So I have to really transform the words and the sentences in a format that the computer can understand. So I have to convert, I have to create a kind of a frequency list, frequencies associated with each of the words and the sentences to understand the patterns much better. So I have to create a bag of words. So that is what is my first step. But of course, when I am creating a bag, I am not even looking at the order in which those words are appearing. Right? It's just a kind of list of words and their frequencies. So it's a variable which indicates whether a particular word has occurred or not. 1 or a 0. If it has occurred, yes, otherwise no. So once we have loaded the data, that is what we have already done. Count the frequency of the classification variable. So I can very well do a table associated with spam dollar, what is that variable? Type. So I want to see how many spams and how many hams are there. So there are 4,812 hams and 747 spams in the whole mails. So overall the list is like when I divide it by 5559, almost 86%, 86.5% of my mails are hams, and around 747, which is another 13.5% of the mails are spams. Now this is what is the proportion of the data. So once I look at that, then I'm moving to my next step where I'm processing the text data for analysis. So the text data is containing so many things, right? In some cases there are words. If you look at the data, there are so many words here. In this text data, when we are looking at the samples, there are different words. There are spaces in it. Numbers are there, the phone numbers, etc. And even punctuation characters, dots and commas, etc. So there are so many things that are there as a part of the text data. So if I have to really do the processing for this whole amount of text data, it goes with large amount of effort, huge amount of time. So I need to remove, especially I need only some important words, right? Why should I use all the words? So I should remove the numbers. Numbers are of not much use for me. Whatever is the phone number, how does it matter to me? Punctuations I have to remove. And there could be a lot of uninteresting words, right? Probably just for grammar purpose, people put them and, or, but. So all these words, in, on, etc. I need to remove all those words so that I can do an analysis of those words which are really creating a big impact. So I have to break the whole sentence into an individual set of words. That is what we are talking of processing the text data. And all these things can quite comfortably be accomplished through a package called TM. TM is nothing but a text mining package. So let's install this package so that we can do this analysis quite comfortably. So I'll install this package called TM, which is doing the text mining job for me. So let me look at TM. So TM is primarily for text mining. So I am installing this TM package. Okay, so this package TM is installed. So once it is installed, I have to load the package as well. Okay, so this package is also loaded. Now, once the package is loaded, my first job is create a corpus. Corpus is nothing but it's a collection of text documents. Now we have 5,559 messages altogether. So we will create a corpus of these messages. Means we will create each message as a separate text document. We'll create a separate text document. So one single message is one single document. Now for doing that, I will take the source. So I'll take the vector source and I'll give all my text documents to it. Text document is I'm giving whatever the spam dollar text. Spam dollar text is the text document that I am creating. So within that, each element of that vector is getting created as a corpus. So here if you see, I am using two functions. One is a corpus, the other one is a vector source. Vector source is actually telling the corpus to use the messages in the vector that I have specified. So I am giving the vector. So if you look at the function vector source, if I am looking at the function vector source, it is vector source of x, a vector of given text. I have to give it as a vector of the given text. So that's the reason I can very well give my vector source as spam dollar text. So this is my vector source. So each one will be a vector, and if you are looking at it, it creates a vector source. So once I give vector source of spam dollar text, it will create a vector source. Now on the top of it, I'll put a function called corpus. Corpus is nothing but it will create, if you look at the explanation for corpus, it creates an R object to store the text documents. So each one will become a separate text document. So it takes a parameter specifying the format of the text documents to be loaded. So you can load them from many different sources such as PDFs, MS Word, etc. So you can load the corpus from any of the location. So you are loading the corpus from here. So that's the corpus. So we are creating a corpus. It's better that I could have saved the corpus somewhere. Right. So probably let me call it as SMS corpus. Let me create this object again. Corpus of all this. Let me take it into the variable called SMS corpus. Now, if I am trying to do a printing of this SMS corpus, if you see SMS corpus, if I am trying to print, which has been done earlier as well, you see that metadata corpus specific is 0, document level is 0, content is 5559 documents. So it's a corpus containing 5559 documents. So that is what is the content of this corpus. And probably if I want, I should even inspect it to see whether the documents have come out properly or not. So I will say inspect SMS corpus. So why to look at all of them? Just look at the first few of them. So let me put 1 to 5. So just inspect this SMS corpus 1 to 5. It's coming out as a plain text document, plain text. Oh, there's no content in it, because I think it's a problem with the way our data got loaded. So it's coming out as a plain text document, but I'm not getting the data inside it. So let me do one thing. Let me reload my data until this stage, so that it becomes more and more comfortable when I have loaded the data. Instead of loading it as a CSV where it has already got converted into a factor, I should load it let me just look at it. Spam as a variable I'm doing a read.csv from this particular location. Here itself, let me set it as, it should not be treated as factors. The text should not be treated as factors. So for that I could use my variable, or where I could use my argument called strings as factors. Strings as factors equal to false. So let me start right away here. Let me see if there is an improvement that is coming out. And I would convert the type, right? Probably spam dollar type is same as dot factor spam dollar type. So I have converted this into a factor rather than converting the other one into a character. Now let me see if I am able to do that job properly. So let me see the SMS corpus this time. Corpus vector of spam dollar text. So this is a corpus that got created. I do a print of SMS corpus now. Yes, it's a code specific, document level 0, content is 5559 documents in it. And if I'm looking at inspect SMS corpus, take it as 1 to 5 elements, I'm not seeing plain text documents. I'm not getting the documents in it. Let me just check what is their head of spam. Okay, so this is there as a part of head of spam. The first one is the type, the second one is the text. Names of spam, type and text. So I am creating corpus. So what is corpus all about? So it's a representing and computing on corpora. It's there as a part of the TM package. Collection of the documents containing the text. That is fine. So basically if I look at the structure of spam, so the text is a character, the type is a factor, even that is pretty much fine. Now let me just check. SMS corpus is nothing but I am creating a function called corpus where I am looking at vector source spam dollar text. I am creating this as a vector source. So this is coming out as SMS corpus. So it is actually containing the corpus information. And I am doing a print of SMS corpus so it is containing corpus specific is 0, document level is 0. So if I just type SMS corpus, even the same thing is coming out. So those are the documents. And then I am also looking at inspect SMS corpus. I'm just taking 1 to 5 observations. So it is telling me that plain text documents, the content is containing 43 characters, etc., but the document is not getting printed. So let me try. So there are approximately 161 characters in this document, 160 characters in this document, and so on. But in reality, I should get the document. I'm not sure why it is coming out like this. So let me just check if it works. So let me move to the next step. So inspecting actually gives me the first view document, but I'm not able to view it here. But let me just go ahead with the next step. So basic text cleaning tasks, let's go ahead with. The first of them is we will use tm underscore map. So where we are coming out with a method of mapping a tm corpus. So we are cleaning up. So we are cleaning up the corpus using a series of transformation functions. The first thing, I want to convert everything into a lowercase letter. So we can see now. So let me try using that, so that let me see if it is directly working out without displaying. So I'll call it as a clean corpus. So wherein I am using tm underscore map as a function. The importance of tm underscore function is, tm underscore map is, it has a lot of methods. It's a kind of a method for doing a lot of transformations. So I can convert all the data to lower, I can remove numbers, I can remove punctuations, all those kind of stuff from the corpus that I have created. So it's a method for transforming a TM corpus. So I am doing a TM map. SMS corpus is the name of my corpus, and I'll say to lower, means everything will be converted into a lower case. So this is what we get as a part of the clean corpus. Then again I want to remove the numbers this time. So clean corpus, I'll take the existing clean corpus, and on the top of it I'll say remove numbers. So I have a function called remove numbers. I'll show what this function tm underscore map is all about. So I'll do remove numbers from the data. So if you look at what is this tm underscore map doing, you'll get a clarity. So it is an interface to apply transformation functions to a corpora. So initially X is my corpus that I am giving, and I am giving a set of functions. So there are so many functions that are there built in as a part of this. So there are different transformer functions that are there, different kinds of transformer functions that are there. So I can, some of them are remove numbers, remove punctuations. So I can even remove a few important words called as stop words. So if you look at the stop words that are already there as a part of this TM package, it will give me that all these words are stop words. In, on, I, me, my, all these are typically called stop words. So I can very well remove for the presence of all these words from my text. So now I'll again say my clean corpus is, now instead of removing the numbers, I want it to remove the stop words. So I'll say remove words, and on that remove words I'll say remove all these words which are actually the default stop words. Otherwise I can give my own list of words also. If I'm not satisfied with this list, I can very well give my own list kept in a C, kept as a C variable concatenation. So all these variables are also removed. All these words are further removed from my corpus. I will also remove punctuation from my corpus. So I'll say remove punctuation from the same, so that all these tasks are performed. So the punctuation is removed, and even the white spaces, only one single white space I want that to be there. So I'll say strip white space. In that case, all the additional white spaces in the messages also would be removed. So I can say strip white space. So now this would be my final corpus. Now if you are looking at the inspect right now, if you are looking at the inspect clean corpus, and let's say 1 to 5 I want to look at now, this is what has happened to my corpus. Okay, so initially something got missed out. So now it is showing well. So hope, good, weak, just checking, K give, back, thanks. So these are the words that are there as a part of my corpus right now. So I have removed all those unnecessary things. So initially I have converted everything to lower. Then on that corpus that came out, I have removed the numbers, I have removed the stop words, I have removed punctuation, I have stripped the white space. So this is a kind of a basic cleaning of the text that I am doing to understand which words are coming out with what kind of a frequency. Then the next step for me is to get into the tokenization aspect, wherein I have to split this whole text into individual components, which is nothing but a set of words. So when I'm using the word token, it's a single element of a text string, which is like a single word in a text. So I'm splitting the whole text into a bag of words. So for that I'll use the function called document term matrix. Using the corpus that I have already created, I'll use this function called document term matrix. So it takes a corpus and it creates what is called as a sparse matrix. Why I call it as a sparse matrix is, it creates, now there are 5559 rows. So it will create 1, 2, 3, so on, 5559 rows. And all the words, word 1, word 2, so on, so many, let's say 10,000 words are there altogether. So this is a matrix with 5500 rows and 10,000 columns if there are 10,000 words in the data, and which will have values of 1 or 0. If that word is present in this particular text, it will have a value 1. If the word is not present in a text, it will become 0. So the matrix is a very big matrix, but only few values of the matrix will be filled. So the rows are indicating the documents here, and the columns are indicating the different words which are existing. And because vast majority of the cells in the matrix are zeros, only very few places you will find some ones, this kind of a matrix is called as a sparse matrix. So the document term matrix as a function will create a sparse matrix. So each cell, now this one, if it is 1, it means that in the second document, which is in the second text message, W1, the word 1 has occurred once. Number of times the particular word has occurred in that particular document. So based on this, I would be able to look at the frequency and the performance and typically how many times a particular word came in all the documents together. So word frequency analysis can be done quite comfortably using this mechanism. So let me try applying that. So SMS corpus document term matrix. So we are using document term matrix as a function. The input that I am giving to it is clean corpus. So after everything is being cleaned, I am giving that input as to the document term matrix function. So if I put a question mark, document term matrix, document term matrix takes X, a corpus for the constructors, and either a term document matrix or a document term matrix, or a term frequency vector for coercing function. Document term matrix, or I can use term document matrix. Let me just check. Let me see, there is one more thing that I can do in terms of clean corpus, where I can take it as a plain text document also. One more step. So clean corpus, I'll take the clean corpus and I'll keep it as a plain text document. Now let me try creating the SMS corpus. Yeah, now it works. Actually, along with all those steps, I have to include making it as a plain text document as well. So one more step that I have to add somewhere here. So tm underscore map, take it as a clean corpus. On that clean corpus, make it as a plain text document. If there are some kind of weird letters, spaces, the word conversion will have a problem. So that's where we'll go with a clean text document, and after that we take it as a document term matrix. Then a sparse matrix can very well be created. So if you look at the head associated with SMS corpus DTM, document term matrix, now it's the dollar operator is invalid for automatic vectors. X dollar n row. So if we simply take SMS corpus DTM, so you will get it as document term matrix 5559 documents, 7925 rows. So the non-sparse entries, so there are only 42,654 entries out of almost 44 million cells that are created as a combination of row and column. 5559 multiplied by 7925. So the sparsity is too much. The minimum term length is 40 words and the weighing is coming out through this mechanism. Now once this is created, this is my data set. So my tokenization is done. I have converted the words. The frequencies of each of the words has typically come out. So let me do a summary of SMS corpus DTM. I don't think I should be able to do anything on that. So no, it is not defined. The summary is not defined for that corpus. Now let me split the data into a training data and a testing data. The same logic which we have used earlier. So out of all the records. So let's take 70% of 5559. So when I'm looking at 5559 into 0.7, it is around 3890. So 3900 I'll take as a training data, the remaining I'll take it as a testing data. So I will take set.seed. Let's say I'll take it as 1000. Then I'll use a variable called train where I am using a sample function 12559, out of which I am taking 3900 elements randomly, where replace equal to false. I am not repeating any of the observations. So out of 1 to 5559 chits, randomly I am selecting 3900 of them without any kind of a duplication. So that is what is my training data. So my training data here, I'll create a variable called training data, which is nothing but I'm taking it from the main itself, right? My main data is spam. So I'm taking from the spam, I'm taking a subset, which is train are the rows, and I'm taking all the columns from it. So that happens to be my training data. Then I will also take my testing data as minus train. So from spam, I'm taking minus train and all the columns. So that is becoming my testing data. Similarly, I can take the document term matrix also. I can take the document term matrix also in the same way. So training DTM, I can take the same way. So we have the document term matrix as SMS corpus DTM. I'll take the train rows and all the columns. Similarly, testing the document term matrix, testing DTM, I'll take it as SMS corpus DTM of minus train comma blank. So this is my training document term matrix. This is my testing document train matrix. Similarly, the corpus also, the clean corpus that I had, even that corpus also, training corpus, I'll take it as clean corpus of train comma blank. I'm taking it as the clean corpus okay, I don't corpus is not a corpus is typically not it's a collection of documents, so it's not a data frame, so I don't need to give the row and column combination. So clean corpus of train. Similarly, I can take testing corpus as clean corpus of minus train. So I have created three different training and testings: the original data, training data, testing data. Similarly, DTM, training DTM, testing DTM, corpus, training corpus, as well as the testing corpus. Compare the proportion of the outcomes, both the training and testing sets, using the prop dot table. So if I am looking at what is the proportion of the spams and the hams in the testing data, so I can very well take the table spam dollar type. But yeah, it's not in spam now. I'm looking at testing data. So let me call it as testing data dollar type. Okay, so there are almost 232 spams and 1427 hams, which works out to 232 divided by 1427 plus 232. The proportion of the spams is approximately around 14% and 86% is hams. So more or less the proportion looks on a similar lines. So with this, my step 6 is done, where I have created a training data as well as a testing data. So we have created DTM also separately for training and testing, document term matrix. Even the corpus also I have segregated between the training and the testing. The next step is, before we initiate the naive Bayes here, we visualize the text data using the word cloud. Word cloud is an important way based on the frequency of the words that have come out in the overall text. There is a pictorial representation that is going to come out. So all the words, so the cloud is typically prepared based on the words, and the size of the word is purely based on the frequency that it has occurred in a particular text. So the words that are coming more and more often have a very high, very large font, and the ones that are coming very little number of times, their font sizes are very, very small. So this is one of the ways that you are seeing nowadays. The word cloud quickly represents which words are more frequently used in your document. So for that I can directly use a package called word cloud. R is typically having this word cloud package, and within that the same function word cloud. This is the name of the function, wherein I can give my corpus as an input, the training corpus that I have created. I'll give the training corpus as an input, and based on that I can even make the learning process happen, or based on that it can generate the corpus, it can generate the word cloud. So it's a simple R function to create the word cloud diagram, and this is there. So the input that I can give to it is a TM corpus object itself. So there are a few input parameters that I can set to it. When I am setting random order is false, so better we check it from here itself. So I have to create a word, I have to install word cloud package. Let me install this word cloud package. Okay, so library word cloud. I'm loading this particular package. Then if you look at word cloud as a function, so it requires words, the set of words. So I'll give the corpus as the input out here. Then frequency, the frequencies of each of the words, and I can also give the scale, a vector of length to indicating the range of the size of the words. I can set the minimum frequency, only those words which have occurred minimum of these many times, they would be considered for building the word. I have to give the words as the input. And similarly, if you see max words, generally by default it's infinite. Random order. The random order talks about plots words in a random order. So if I don't give anything to it, it will take the random order as true and it will plot the words in a random order. But if it is false, then it is plotted in form of decreasing frequency. Similarly, random color, by default it is false. So there is some specific color that it is taking. So if it is true, then the color is chosen based on the frequency. If I am setting it as false, It means the color is chosen based on the frequency. If it is true, the colors are completely random. So all these kind of things are there. Color the words from the least to the most frequent kind of stuff. So you can get different kinds of word clouds altogether. So let me just go ahead and create a word cloud, a simple quick word cloud where I am giving the corpus object altogether, which is my training corpus. So I'll give the training corpus as an input, which is also a list of words. Nothing else, I can just give this much sufficient. By giving this, there is a word cloud that got created. Now, this is the reason I want to specify from minimum frequency, because you see there are so many words that are there. So the cloud is looking too crowded. Now this is where I want to focus on improvising this a little bit more by setting the minimum frequency. So this is where I can say minimum dot frequency is equal to, let's say, 25. At least a word should come 25 times to be included as a part of the word cloud. Now let me see if there is some kind of an improvement. Yes, only this is my word cloud now. Right, so the words which are coming more number of times, they are getting shown with a bigger font. The words that are coming fewer times, they are shown with a smaller font. So this is how I am able to generate my word cloud. Every time I generate a different word cloud altogether. So the random order is there. So the word cloud gets created in different fashions, but the sizes, frequencies will remain more or less the same. So this is how I can very well look at my word cloud altogether. So if I keep repeating it, I get different representations because the random order is typically being generated. But if I don't want the random order, I can very well set the random dot order equal to false. So this is one more step. I have generated a word cloud with my data now. Now compare the word clouds for the different groups of outcomes, so that for training data as well as for the testing data, I really want to see what is the word cloud looking like. So I want to look at spam data separately, where I am taking a subset, right? I am setting a subset of the training data. I am taking a subset of the training data where the type is equal to spam, right? So I am taking a subset of the training data where the type is equal to spam, and I am also taking it as a ham data, which is a subset of the training data where the type is equal to ham. I really want to see whether the words are more or less similar for both of them, or are they completely different. So let me use the word cloud now. So instead of talking about the training corpus, I want to create the word cloud based on spam data $text. So for this one, I want to create a word cloud. For spam data $text, my word clouds are showing call, free, now, mobile kind of words coming out more frequently. But if I am trying to create the same with ham data $text, I'm getting a different set of words altogether, right? Probably call is not there out here, right? And mobile is also not looking, call is there. So some of them are there both in the spam data as well as in the ham data. But for some of them, they are not clearly visible. So which means I can see that there could be a difference in the spam data versus the ham data. So this is one more thing. So if there is a clear difference between the two groups, then probably I can very well say that the naive Bayes model can very well be helpful for understanding whether something would be a spam or a ham, because they are dependent. If a particular keyword has occurred, then this might be a spam. If the particular keyword has appeared, then it might be a ham. So when such kind of thing is coming out, then there is a possibility that I can use the naive Bayes quite comfortably. Otherwise, my naive Bayes also goes into limitations. Then we are doing a data preparation with respect to creating an indicator features the frequent words. Creating indicator features for the frequent words. So more and more frequent words, I am transforming the sparse matrix so that it goes as an input to the Bayes classifier. So that's the next step. Now I have a sparse matrix containing the list of text out here as well as the list of words out here, and here it is showing how many times that particular word has come out as a part of this particular text. Now I am transforming the sparse matrix into a data structure so that it can be given as an input to the Bayes classifier. Now this is where the TM package also has another function called find frequent terms. So find frequent terms as a function will actually identify those words which are very frequent. So I'll give the document term matrix as an input, and it will return a character vector containing the words appearing at least a specified number of times. So I have to really give the document term matrix of the training data, right? I have called it as a training DTM. So I'll say find frequent terms, wherein I am setting training DTM. I am taking the document term matrix, which is a training document term matrix, and I am setting minimum that should be a 5 times that particular word has occurred. So this actually I can save it to a dictionary if I really want a list. So these are almost 1177 words which have occurred for a minimum of 5 times. So all these things I can create it to a dictionary. I am calling it as SMS dict, wherein I am using a function called dictionary. Dictionary is a kind of a data structure which will talk about those values that should come as a part of my document term matrix. It's a data structure. It is allowing me to specify which word should appear in the document term matrix. So I am using my find frequent words, whatever the words that have come as a part of the find frequent words, I am saving it as a dictionary. Right, whatever the words that are coming out as a frequent words, I am saving it to a dictionary. So my SMS dictionary otherwise let me give directly. So find frequent words is a kind of a list that I have created, which I would be using as a part of my training. So once I have created this particular list, now let me see. The naive Bayes classifier is typically trained on the data with the categorical factors. So the sparse matrix is indicating the count of number of times a word has appeared. So that's where I'm changing this to a variable that indicates yes or no. So that's where I'm using a function which will do the conversion part. So I'll typically say convert count. So I want the count to be converted into yes and no. So for that I am creating a function. I'll create a function of x where I'm assigning x as if else x is greater than 0, which is the function is if the number of counts is greater than 0, I'm taking it as 1, otherwise I'm taking it as 0. So the x is becoming either 1 or 0. Now that x again I am converting it into a factor. So I am calling factor of x where the levels of that particular factor where the values are either 0 or 1, and the levels for that I am setting the labels for it as no and s. So I am taking them as the labels for it, I am setting them as no, and along with that I am also setting that as s. So 1 means s, 0 means no. So that's how I am setting the labels for it, and I am returning the value of x. I have put double quotes here. Again, let me start the process. Convert count function x if else value is greater than 0, 1, otherwise 0. X is coming out as factor of x where the levels is 0, 1, and the labels are set as no or s. So I am closing the function out here. I have to close the bracket here as well. So let me rewrite the function again. Let me close the bracket out here. Okay. So this is how this function is created. Now I'll take my training data. I'll create some variable called SMS train where I'm using the document term matrix. Right, I'm using the document term matrix which is created based on only the frequent words, not all the words. So I'm simply taking training corpus, and within that training corpus I'm taking only that particular list. So I'll say list of dictionary equal to, I'll take whatever this function has given as a part of my dictionary. So I'll take it as find frequent terms, this one. Right, I'm taking this particular stuff as a part of my SMS train. So my SMS train is created. Similarly, from the testing corpus, I'll take it as SMS text test. Again, I am using the same document term matrix wherein I am taking testing corpus, and again I am seeing the same set of words. So I am saying list is list where dictionary is equal to the find find frequent terms of this. I'm closing this, which will give me the SMS test. So there are frequent, so I'm looking at first of all frequent terms which came at least 5 times. So I'm building a document term matrix with those set of values, and now I am applying on this training data, which is a new document term matrix containing only the most frequent terms that have come, I will take yeses and nos out of it. So this is where I can use the apply function, right? So the same SMS train, I'll remodify this SMS train, wherein I'm applying to the same SMS train the columns. So I'll set margin equal to 2. For this particular columns, I'll use the convert count function. Convert count function I'll apply for each column. Each column is nothing but SMS train. Here is my document term matrix, which is a sparse matrix. So for each column, which is means for each word, it will actually set it as either yes or no kind of stuff. So that is how my SMS train is getting computed. And now if you look at the SMS train, first let the SMS train data get computed. So because there are so many columns, it's taking too much of a time to apply that convert count function, because convert count, what it is doing is, depending on whether it has occurred at least once or not, it is taking 1 or 0, and if it is 1, it is making it yes, otherwise no. So quickly look at the head of SMS train to see what has actually come out. You could see all these things. Yogasana, yoding, yogi, young, younger. So these are all coming out as no's, some of them coming out as yeses. So that's how the conversion has occurred. Similarly, I can do the same thing. SMS test. Also, I'll take apply. SMS test. Margin equal to 2. For each column, I want to apply the same. And convert count is the name of a function that I want to apply on the top of it. So this is making my testing data also in front. This is giving me my testing data. Now here my model is ready for taking the naive Bayes input for classification purpose. Now this is where I'll start training my model. Naive Bayes is there as a part of E1071 package. I think it should already be there on my system. So library E1071, I'm simply loading this library. Yes, the package is already existing. So once I have installed the package, I have loaded it. Use the presence or absence of words to estimate the probability of the outcomes. So that is what we are doing here. When we are training the model for the data, it is using the presence or absence of the words to estimate the probability of the outcomes. So when we are training a naive Bayes learner, and whatever the learning that is done now, it would be used for classification in separate stages. So the training is happening as a first step and the predictions are happening as a second step. So in the training, I have to give my data from the training. Then I'm also giving the factor vector of the class for each row in the training data. And I'm also setting my Laplace estimator. By default it is 0. But if at all I want a much better result, I would go for 1, where the counts all the cells would be increased by 1 to make sure that 0 probabilities don't come up as a part of any of the mechanisms. So we will call it as model. The model, for the model we are using naive Bayes. Naive Bayes is the name of the function where I am taking my SMS train, which is this particular data, and for this SMS train I am also giving the type that is associated with the variables, whether it's a spam or a ham. So that type I have to specify. For each of the variables I have to clearly specify my type. So I have already my training data So training data, or probably we have taken, yeah, the training data dollar type. So I have taken the SMS train along with the training data dollar type, which has given me my model. Okay, the model is created right now. The type we have already assigned to it. Now you can look at the model to see what it has given. So it has actually given the probabilities of each of them for each of the word. What is the probability that it is going into a ham? Ham is no, ham is yes. Spam is no, spam is yes. So on the training data, it has actually brought out what is the probability that it belongs to this particular type versus the other type. So in this case, if I wanted something more better, it's better that I set my Laplace indicator as, instead of 0, set it as 1. Now you can very well check the scopes of all these zeros will be removed when your model is having a Laplace indicator of 1. Now when you are checking the model, so none of them are zeros now, they are slightly positive values itself. Now based on them we are doing the prediction. So where we are using the predict function, the model that we have created just now, and now I have my testing data also. Based on this model I have my testing data, which is nothing but testing data. But for this testing data I don't want to use the classifier. So I'll take it as testing data dollar text. So I want to predict the model on the testing data dollar text, where the type I am setting it as class. So based on the text it will try to predict which one is going into a, so I have to give it as the testing data only, not dollar text. Oh, the testing data is nothing but SMS test, not testing data. So it's SMS test. Okay, so it is doing the prediction of the model on the SMS test data. Now once the model is created, I can very well see how many of them are correctly classified. So this is the performance that is coming out on the test data based on the learning that it has done on the training data. So it has taken too much of a time to do the prediction part. But if I see P now, what it is, so a lot of things are getting classified as spams or ham. Now I can very well create a table, right? The table, now I can very well use what is the prediction that I have done. P is my predicted value, and what is my actual values. The actual values are coming from the original, right? So I'll have it as the testing data dollar type. That is my actual testing data dollar type. So based on that I am seeing that 34 of them are wrongly classified. Out of the total, 1424 are predicted as ham, but reality also they are ham. 201 of them are predicted as spam, they are also spam. Whereas 31 of them have been predicted as ham, they are good messages, but they are actually spams. So this is a dangerous thing for us. And at the same time, even this is also dangerous. I am predicting these as spam. They are not getting delivered into my inbox. They are going into my spam folder, but 3 of them are actually ham. This is even more a serious error for me out here. So I want this number to be reduced to whatever extent possible. So this is what would be my next focus as a part of the improvisation of the model. So as a part of the improvisation of the model, I can very well set my Laplace estimator as 1, 2, 3, so on. And based on that, I need to further evaluate. So I have to make sure that this number comes out much lesser. So I'll choose that particular combination for the Laplace indicator in such a way that my overall spam, this particular variable is going, this particular column will come out to be as least as possible. I would prefer this to be a 0, which means I should not consider some particular mail as a spam, in fact which is a ham. So I would try to work out a little bit on the Laplace indicator values to make sure that I get a much better result. So that's how the process will keep continuing. So this is what is a typical process where we have understood the text related mining aspects along with clubbing it as a part of my naive Bayes algorithm. So this is what I wanted to cover as a part of this session. Right, we have dealt all these aspects with taking a good example from the text analytics part. You have to practice this much more with another set of data which is indicating a lot of text related stuff. If you have any further queries, you can feel free to get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at the email address that I have provided. Thanks a lot for listening to this session. Thank you very much.